Okay, I'll continue with the ICA. So, among all the ICA algorithms, one of the naturally arising solutions is the maximum likelihood ICA. Considering that, if you remember the structure we already had in this slide, so there was a filter. That filter could be named, for example, W, and we were trying to get the signals from the observations from the sensors, and then trying to figure out what are the parameters of this linear system, W, in such a way that a kind of process using these assumptions, which is independent actually, to be realized. And we need to feed all the priors that we have into that processing in order to be able to separate the sources. The idea is actually taken from a Dharma theory. What is the Dharma theory? Let me write it down. I'm not sure if the spelling is right or not, so it's a French word. I hope it's right. So that's a Dharma theory. If anybody knows French, maybe it's I'm pronouncing differently. Okay. So the theory is, in a very simple case, if you have, for example, y1 as the linear combination of the sources S1, S2, up to Sn, and for example, y2, these are the sensor signals, observations. As, for example, B1, S1, B2, S2, B and Sn. If for every I, Si, for example, assuming that there is an I in between of any of these polynomials, so assuming that there is I, which is not 0, so it means that we have Si somewhere. If for that Si, the corresponding Ai and Bi are not 0, there should be some value for it. And if y1 and y2 are independent, that's a sign for independence. This is the sign for the independence. So if y1 and y2 are independent, then Si is a Gaussian. Let's translate it into something that we can understand it much easier. One consequence is that S's, so the signals which are not Gaussian, so I don't know how to write it, S apostrophe S, S's, or a single signal or one Si, every Si, which is not Gaussian, exist in both y1 and y2 without leaving y1 and y2 independent. What does it exactly mean if you refer to the central limit theorem, CLT? You know that if you have sufficient number of the random variables combined together with the same PDF, same mean and same variance, whatever that PDF is, we don't care about the type of the PDF. If there are sufficient number of the variables, random variables, combined together, the combination, the result of the combination will turn toward Gaussian. That's the central limit theorem. So for example, if you have sufficient number of the speech signals, assuming the speech signal is you're having the same PDF, which it is, with the same mean and variance. If sufficient number of the signals are combined together, the result of the combination will turn toward Gaussian. And it's true for all types of the signals. That's true for all types of the signals. Now it means that if you have these sources, if you have, for example, y1 and y2, and you want to get the output as estimation of S1 and S2. So first of all, you tell me which of these PDFs, y1, y2, or S1 and S2 is closer to the Gaussian. First of all, you tell me which one of this set of inputs or the output PDFs is closer to the Gaussian. Based on the CLT, these should be closer to the Gaussian, because they are a combination of S1 and S2. If we ignore the noise, which is itself Gaussian and it's added, even ignoring the noise, these y1 and y2 are more close to the Gaussian than the outputs. So it means that if we can find a solution, W, in such a way that tries to make the outputs as farthest as possible from the Gaussian PDF, we are actually getting to the single source. We are going close to the single source. So if I can try to run away from the Gaussian in the output by manipulating the parameters in this W, and to make them get far away from Gaussian, I'm actually getting far away from a combination and getting more toward the singleness. Because CLT is telling me that when you have same essence, same gender of the PDFs combined together, always by adding one source, it's getting more Gaussian. One more, getting more Gaussian. So if you are getting far away from the Gaussian, you're actually getting more close to be a single source. Did you get it? That's the result of Dharma Theory. And that's how we try to find out this W as a demixing filter in the ICA, to get far away from the Gaussian as much as we can. If we can do that based on any optimization problem, we don't care at this moment about the optimization problem. That's for further theoretical stuff if you want to go through. You should get the notion of what ICA is. For the algorithms, you can go through any tutorial and find it out. But the idea is try to run away from Gaussian as much as you can. If you can do that, you are getting more close to be a single source in the end. That's the idea of ICA. Now I'm writing down the maximum likelihood solution to the ICA problem. So you got the idea. Yes?
If the signal source itself has a PDF of Gaussian?
If the signal itself is a Gaussian.
Yeah, single source.
It turns out you are just allowed to have one Gaussian signal among all. So it can be happening in such a way that you have just one single Gaussian added to both of them. And that's all. It is not possible. So if this, because of the noise, the only possibility that it turns out is just you can have one noise, which is Gaussian, but the other signal should be for sure non-Gaussian. If you have more than one Gaussian signal added, you will not be able to use the ICA for that. And it's, because of the geometrical explanation, it's also clear, because ICA is nothing but a PCA plus a rotation. So you do the PCA, you decorrelate the directions, the components. So the first is we have independence. Independence, as I mentioned from the cumulants, contains the first independence, the first moment or first cumulant independent, which is the mean. The second order independence, which is variance or covariance. The third order, fourth order, and so on and so forth. PCA is just the second order, the variance, projection of the variances over the to make the maximum variance. And the components should be independent. So they are not independent, they are actually orthogonal. That's just the second order independence, which is called orthogonality and PCA. So it means that if you can get independence, for sure, if you make two sources, two y1 and y2, to make them independent, you have already done the correlation. It has already been achieved. But it's not true the other way. From independence, you can always infer the decorrelation, but it's not the other way. Because decorrelation is just the second order independence, but independence here is for all the cumulants. Not just the second one, but also the higher order cumulants. So the second one is nothing but PCA. So ICA means first you do a PCA, decorrelate the directions and components, but it's not enough. You need to have a kind of rotation. Finding that rotation is the problem. So that was just an emerging question, and it was a very good question, so I had to explain it. Now, what is the solution for the ICA as a maximum likelihood problem? So you know that we are going toward the independence. Independence is a very hard condition to realize. There are thousands of the cumulants. How to get through that? Directly is not possible. Indirectly, yes. We get some of the signs. There are some indications, some measures that if you can optimize those measures, you will get closer to the independence, but in an indirect way, not a direct manner. And it's simple, you know, just from the ideas. One of them is try to maximize the kurtosis of the signal in the output. You have Y1 and Y2 combined together, the combination of S1 and S2 and of the sources. Try to find out W in such a way that every single signal in the output, the PDF of it, gets peakier and peakier as possible. So maximization of the kurtosis, which is the force cumulant of the PDF, maximization of the kurtosis is one of the indications of getting the independence, which is one of the algorithms in the ICA. Try to maximize the kurtosis, or the force or the cumulant. That's one ICA algorithm. So, assuming that this is the linear system of equations, observation, mixture matrix, and the sources, and all the assumptions we already made. So, we have x for let me for the time index, I will put it as a supers index. So x1 to xt. That's the time index for the observation signal. When I use it on the bar, it means it's a vector. x1, x2, x3, so whatever number of the microphones is. So, the likelihood function of these observations for the matrix A. Because if I can figure out what is exactly matrix A, I would just make the inverse of A and get the signals. So A, how to get A is the crucial thing we have to do. We define that as a log function log of the likelihood, which is the P of x given A. So we need to estimate A as a maximum likelihood estimation of the A. Something that maximizes this likelihood function. And the capital letter with the underbar is always a matrix. It's always a matrix. And here, based on the assumptions of ICA, this matrix is full rank and quadratic. So, one of the requirements is that, now assume that the PDF of the source is Q of Si. That's the PDF of every single source. So the joint PDF of the sources, based on the independence theory, should be the product of all the sources. If you have n sources, it should be QSI. That's the definition. We need to have independent sources. Independence respects this equation. So, is the observation X, which is AS. You have an assumption for the signal to have a kind of PDF, but what you observe is X. So you need a PDF transformed to another domain, from the input domain to the range domain. Input domain is S, the range domain is X for observation. Based on the PDF transformation, we know that so let me show that at this moment. The PDF of the observation depends on the PDF of the signal with this equation. Determination is the determinant of the matrix A, and this is the product of the PDFs. This, you probably know that from the probability theory. What we are looking for is W, which is A inverse. This is what we are looking for. So, the log likelihood function, looking for W instead of A, replacing it, will be the log of P of X for W, replacing this stuff here. You know that when you have W as A inverse, determinant of matrix W is 1 over determinant of matrix A. So, if you put this as the determinant of matrix W, and then considering that S is supposed to be A inverse X, which A inverse is W, and then write down the log likelihood again, you will get this. A sigma over 1 to n, the log of QSI, but we replace it with this one. For every single one, we need WI. This I, WI. The entire S, entire W. Okay, that's the log likelihood function. Generally, people use a kind of exponential form for the input PDF. So, Q of Si, it can be everything, but normally they use exponential form, and it might be clear why we use the exponential form here. Because the log of exponential is the simplest thing you can have. Okay? We'll just get this after doing the log. And doing the summation is just doing the summation over the h of S. Many cases, and it makes sense. Many of the sources, they follow the exponential family. Many of the sources follow the exponential family. Laplacian, gamma, generalized Gaussian, the Gaussian itself, Rise, many other PDFs, they are all Gaussian form. For example, the Laplacian is, for example, like this. With a kind of, you can put, for example, a gamma parameter or something like this here. So it makes sense in many cases. And for the discrete signal, for example, which is sparse or which has a high kurtosis, that exactly makes sense. for many real signals, the exponential family makes sense. So you should choose something, a kind of function over this in the exponential in the power. Then the log likelihood will turn out to log of determinant of W because of this minus sigma y to n h of s, which s is wx. So the maximum likelihood changed to maximizing this function over W. The only thing you have to know is when you choose the PDF, an appropriate PDF for the signal, what should be this h? For the Laplacian, I just wrote down as an absolute value, simple absolute value here. For many other cases, you know exactly what kind of signal you're dealing with, what's your application. So you can choose the best edge for that application that you have. Maximum likelihood. So if you have, now we see that it should be respected for all the times. Time 1 to time, all the times. Assuming that every observation that you get is independent from the previous observation in time, I mean. Then P of x as, how to show that from 1 to t, for example. Then it's, because they are independent, then it's the product over the time of every single P of x, t, for example. You write it down like this. Then the log likelihood function changes to, for this x, I don't know how to write it down, but just I put it 1 to t. It means that I'm talking about the sequential in time. So the log likelihood for the entire time samples of the observation. This is for localized in time. This is for the entire time, the entire signal in the time. For the W, can be written as the summation over every single log likelihood. Every single log likelihood from this block here. Is that clear so far? Everybody can understand so far? So that becomes T log of determinant minus 1 sigma over the time and the second sigma over the number of the sources. So what I have there, I just write it down. I think it's clear. So but in general, we don't like the functions to go toward infinity when the time goes toward infinity. Here. So what we can do is to normalize it. We can just normalize this. Using the normalized version of that, maybe I can write it down or up using the other. So you have already written that, so I can just this part. If you have already. After doing the normalization over the time, and you tell me, what is the normalization over the samples? You have a lot of smoothing over the samples. What is it? What is the definition of smoothing over the samples in time? Everybody knows probability and statistics. Smoothing over the sample is taking the average. What is taking the average? What is the time average? What is the name for it? Yes, mean, expectation. Just take the expectation of that part, and it's a smoothing. Getting rid of the time. That's all, taking the average. So you take the average of maximum likelihoods over the samples. How many samples you want to have in your block of the time? The more, the better. Why? Because when you're taking the expectation, the more samples give you the better expectation of the mean. Is that true? But in general, expectation is the mean. So I'm trying to get rid of the time parameter because that parameter is problematic. When time goes to infinity, then you don't know what exactly you have to do. But you know that you're doing the process over the block of signal for a noun period of time. Just take the expectation. And that's after doing this expectation. So over the time t, the period of time, the first part, you will get rid of the t that already have because it's t. Then in the expectation, you divide it by t, and from the numerator and denominator, you will lose it. It becomes log of determinant of w minus expectation over that period of time of h of w. So the local w for the time. That's all. And you know that the maximum likelihood is asymptotically unbiased. So it's a very good estimate. And efficient. So it means that when time goes to infinity, it's actually getting close to the real minimum. The expectation goes to the error of the expectation is actually going to the minimum. So that was the maximum likelihood solution for the ICA. You get the W, and that's exactly what that works here and separates the signal S1 and S2 for the maximum, for the most independence based on this PDF. Initially, people had problem to use the independence as a criterion. They tried to have decorrelation, but in a nonlinear version. So in a single decorrelation, you are getting the signal 1, signal 2, and you just try to make the cross correlation, which is the expectation of one over the other, to minimize that or to make it 0. So that's the decorrelation. But decorrelation is just a second order independence. So people said that you can get the higher order, an approximation of the higher orders independence by using a nonlinear form of the signals. For example, if one signal yi and the other one yj, like here y1 and y2, they tried to decorrelate yi3 yj, or the other way around, for something that they can write down what is exactly that expectation, then trying to decorrelate, so in a nonlinear form, or a function of them. So if you're not able to make the independence, at least we can make a function, a nonlinear function over the y1 and y2, and using this f and g for yi and yj, try to decorrelate fy1 and gyj, something like that. So these are different methods that came up in the beginning, but finally they all turned out to, this is the maximum likelihood ICA, which I already explained. They turned out into the various ICA algorithms, which I explained already, like the maximum kurtosis and neg of entropy, because entropy is exactly the same as Hilbert divergence, as I already mentioned, and you saw that it has a minus in front. So if you can, the neg of the entropy, if you can make it maximized, it means that you are separating the sources based on the independence. So people tried different algorithms, fast ICA and so on, but probably I will make an auxiliary note for you because it's more mathematics. If you want to go through, I'll just show you in simple examples that how it works. But out of the scope, not the scope of the lecture today, but maybe it's more detailed in mathematics. I don't want to bother you with mathematics. There are three different approaches for BSS in general so far. One is ICA, I already mentioned, the actual initialization of the BSS, that considers the sources to be statistically independent, and you can just have one Gaussian source, not more than that, because of what I explained. The second method is a sparse component analysis, which assumes that the sources are independent. An extra prior is that the sources are also sparse. And the third one is non-negative matrix factorization, which is also applicable for even one single mixture of the sources. So it also assumes that if you factorize the observed signal, then this factorization gives you the positive factors, so, or non-negative factors. And it's a fact. So they use this fact to come up across with different methods. In general, beamformer and BSS, they have many things in common. I skip over this slide because you can just go through it afterwards. For the convolutional mixtures, we have the most problem for the BSS is for the convolutional case. For the instantaneous case, you can use the ICA very easily. For the convolutional mixtures, which in the real signals, they're normally convolved with the environment as a filter, and then you're observing the signal in the sensors. Then you have to go to the frequency domain or a transform domain to make it as multiplication, to make it simple and to make it look like what we had in the instantaneous ICA. But the problem is that using the ICA, then you have the problem of permutation, and that's problematic. Why? Because in every frequency you need to have a signal, and this signal is chopped into the different periods, time periods, short time periods. Then you do the short time Fourier transform. You get a spectrum of the signal for that period of time. But the ICA is applied to every single frequency bin. But after doing the ICA over every single frequency bin, there is a permutation problem. So in one period, you have the permutation in every frequency bin. So that may cause a problem that, again, they are mixed, but in this time, in the frequency. And then for the coming frame, the next frame, if in the previous frame you have not estimated the permutation correctly, then you are combining two different frames, two consecutive frames with different sources. Did you get what I mean? Let me explain it very simply here. You do the The signal is coming. You chop the signal into different frames. This is, for example, frame 1, FR1, FR2, FR3, and so on. For every short time frame, you do the STFT for the signal, for all the signals, Y1, Y2, whatever you have in the observations. So that gives you, for each of these Y1, Y2, and so on, that gives you the spectrum over the frequency of F1 until, for example, like F. You apply the ICA for every single frequency. But here, Y1 is combination of S1, 2, and 3, and so on. When you do the ICA here, you get the S1 estimate, S2 estimate, and so on. Also for this one, and this one, and this one, and so on. But they are permuted. And the permutation for this frequency might be different with this one. Now the next frame comes. If you want to get the source 1 out of that, you need to connect the S1 from this frame to S1 from this frame, the next frame. But if they are permuted, and you cannot estimate what is exactly the permutation, then you might connect S1 from this to S2 from this one, and then S3 from the other one. So finally, when you get the signal, connection of all of these patches of the signal, and transfer it back to the time domain, you will not get exactly the source 1. Because you have in the middle, in every single frame, in some of the frequency bins, you might have made a mistake and connect the signal S1 to some other, the chops should be from the S1, should be from the S2, S3, S whatever. So did you understand what is exactly the problem of ICA when we use it in convolutional form? In convolutional form, you go to the frequency domain, and you have for every single frequency the problem of ICA, which is prone to permutation. And connecting these frames might be a big problem. That's why you have thousands of papers that they just try to find a solution for the permutation problem of ICA in the frequency domain. You have to find a solution for that. In SCA, or sparse component analysis, these are just single frame, single slide information. You already know the ICA. SCA just is adding a sparsity. What is a sparsity? A sparsity says that it rarely happens. That's a fact. That's a statement. The statement for the first time brought up with Georgine and Ricard in one paper in 2000. It rarely happens that two different sources in short time Fourier transform, two different sources or more different sources occupy the same frequency bin at the same time. That's the statement. So it means that every single bin should belong to S1 or S2 or S3 or whatever, and not S1 and S2 and combinations of them at the same time. But that transform domain we should already find it out. What is it? For speech is the short time for transform. We already know that. For many other, for image, DCT transform. So every single bin either belongs to the first source or the second source, and not both of them. That's the idea of sparsity. The measure of that is called WDO, or W disjoint orthogonality. Disjoint orthogonality. So jointly they cannot occupy the same bin. They are disjointly orthogonal. And that's for every single frame, every bin. That rarely happens that two different sources get the same thing. And for the speech case, it has been already investigated by the researchers that is true. For example, we see here for 3 number of the sources, it was correct for more than 87% of the time. For 5 number of the sources, it was correct if you have the frame size of like this, for example, 512. For more than 78% of the time, this fact is correct, and you can just use it. Even for the, the reverberation environment, which is very, the harsh environment, even in that case, you see that the fluctuation over the value that you got from the anechoic case is very few, so it's actually ignorable. So we can say that in most of the cases, the fact of the WDO disjoint orthogonality is a true fact, and we can use this prior for the SCA algorithms. And there are a lot of algorithms in SCA that they use this fact and they try to separate the sources, like the duet algorithm, which is very famous, lost algorithm, and there are some sub-algorithms that we have developed, for example, for SCA. The idea of linear inverse problem that we already mentioned, this is something that holds for the entire BSS theory and the beamforming theory. If number of the sources are more than number of the sensors, the problem is called overdetermined. If they are equal, it's called the even determined. The ICA is the solution. If it's overdetermined and if it's underdetermined, mathematicians, they say that for overdetermined there is no direct solution, and for underdetermined there is infinitely many solutions. In order to find a unique solution, we should have a kind of idea, a prior. So the problem only happens in these two cases, which we should find a solution for that one, the second one, which is overdetermined, or for underdetermined, among the infinite many solutions, finding something unique. Turns out that the sparsity of the sources as a fact gives us the unique solution for the underdetermined case. And for all the cases, mostly the error function is the same as what we already had, is least square error. Definitions of this error you can see here. There are different norms for the error that are involved. Norm 2, norm 1, norm P, norm infinity. And if you have, for example, the covariance of the error, then the best norm that you can use is the covariance norm. So you're trying to find out the inverse of H, such that when it's applied to X, you get Z. And that's called the energy norm. It depends on whether you have the covariance of the error or not. And mostly, the covariance of the error is nothing but the covariance of the noise, because noise is the error. So the L2 norm is the solution of this problem, and it's a convex problem. Here, I've written the underdetermined and overdetermined case, the least square solution for the X, for the energy norm case. So if you know the R, you can easily find out what is the least square solution for that. But if you remember what we explained in the beamformer, we said in beamformer that the signal in the microphones is the array manifold vector times the signal of interest plus the noise. And the array manifold vector was based on tau 1, tau m for every single frequency. And these tau values is the time difference or the time value that it takes from the source to come to the microphone related to that source. So if you have one source, the time that it takes from the source to come to the microphone number 1 is tau 1. To microphone number m is tau m. And it depends on the geometry of the microphone. Okay? That was the array manifold vector. and is S, the source, plus a noise. It's the same as what we have in blind source separation. The only difference is that by knowing the geometry, we are just assuming something for the matrix A. Because we are assuming that this is matrix A, the mixture matrix. So we are indirectly saying that we have something for the mixture. So it means reducing one step from the blind source separation. Because in blind source separation we had two steps. One, estimating the mixing matrix. The second one, getting the inverse of the mixing matrix times the observation to get out the signals. In this case, you are assuming that you know already based on the geometry, because you know the geometry, you assume that this is already known. Then the problem that you solve is nothing but the problem of BSS, minimizing the energy. So here is just minimizing the energy, the variance, and to get this result. And this result, just check it with the overdetermined and underdetermined. You have one source and more sensors. What is the problem? Over or underdetermined? This is unnown, this is noun. You have more nouns and less unknowns. The problem is overdetermined. Look at the overdetermined answer. S transpose R something inverse times this. And look at this one. And put H, replace it with array manifold vector. The size of array manifold is transpose. So this is the V transpose. V transpose. R is the covariance of the noise. Inverse. So sorry. V transpose R inverse. V0 is entirely is inverse. It goes to the denominator. And the rest is H transpose. So this is the transpose already. So when you say H transpose R inverse. And that's the denominator. So this is the W that times the observation gives you the signal. This is the W that times the observation will give you the signal. Did you get it? So beamforming is just a special case of blind source separation. That we are assuming, here I've written the beamforming and the source separation together. That we are assuming the filter, the mixture is already known with the array manifold vector. But we know that it's a very crude assumption because array manifold assumes that everything is directly coming to the microphone. But in convolutional cases, it's not like that. It goes to everywhere and you have reflections from everywhere that makes that direct assumption incorrect actually and not accurate. It should be actually the filter. And the blind source separation assumes the filter in general sense, not just a single attenuation. Because e to the power of j omega or j omega tau, it means e j phi. And phi is nothing but just the delay or the phase shift. Phase shift or delay. So in beamforming, it just assumes that there is a delay between the source and the microphone. That's true, but it's just for the direct signal. You have both the delay, attenuation, and many reflections. So that was how they are corresponding to each other, beamforming and the blind source separation. And for the SC, it's just an example that if you have a combination of the sources, if you can even figure it out very simply from the mixtures here I've written, I already wrote it here. If you have, for example, X1 as a combination of A1, S1, A2, S2, and so on. And X2, B1, S1, B2, S2, and so on. The assumption for the SCA is sparsity, so one is active at a time, and not all of them. So it means that one is active, A1, for example, is active, and all the others are 0. So X1 becomes just A1, S1. And X2 becomes B1, S1, but the rest are 0, because it's the assumption that only one source is active at a very short period of time. At least for the STFT case, for every single bin, we can write it down like this. So what is this? It's just X1 over X2 is A1 over B1. So if you draw the X1 over X2, X1 and X2, the scatter plot. What is this? X2 is B1, A1, X2. That's a line which passes from the origin with the slant B1 over A1. That's the origin line. It's in reality, it actually works. In STFT domain, it really works. So if you have more number of the sources, so X1, X2, A1, B1, S1, and so on. So for one time, S1 is active. The other time, just S2 is active. So you get B2 over A2 as another line. Then you have B3 over A3 as the third line if you have 3 sources. So you have 3 sources and 2 sensors, X1 and X2. It should give you 3 different lines. All 3 are passing through the origin. 3 lines passing through the origin. That's the meaning of sparsity. And that's the idea of sparse component analysis. So you just get the data, take the scatter plot, assign the scatter plot the points to the line. So you do the regression, the linear regression for the data points. Assign the points, each of the dots, to one of these lines to say that, okay, that belongs to S1, that belongs to S2, that belongs to S3. And then classify them. You get S1, S2, S3 differently. That's the idea of source separation in the SCA case.
How many more slides?
These are just the algorithms to mention. I don't want to go through that. I explained the idea, and this is the last slide. This is the last slide, which is NMF. I'm just explaining what NMF means, that's all. After explaining about the ICA and SCA, NMF just recently, after 2000 actually, it started to emerge. But recently, I can say that the highlighted version of the BSS is just NMF. And the idea is just in one simple explanation here. You have the observation, the same as what we did in SCA. The spectrum, the short time Fourier transform, for example, is one idea. You can have STFT kernel or whatever kernel, as you like. You just assume that this is factorized into 2 things: the dictionaries and the weights associated to the dictionary atoms. So how many atoms in the dictionary? As you like. While training, you can take thousands of atoms, you can get 100 atoms, depends on how much resolution you need. For STFT wavelet, the atoms are already predefined, but you can have non-parametric, which means that the number of the atoms in the dictionary can increase as you like. So you have the atoms and the gain of those atoms, but the atoms are positive, non-negative, and the weight should be negative. So this is also positive. So it means that the spectrum that I get, I try to factorize it into 2 things: atoms and the weights, in such a way that times of, the product of these atoms and the weights will give you the signal. So it means that the Kullback-Leibler divergence between the PDF of the signal and this factorization should be minimized. That's the idea. Subject to what? Subject to the constraint that both the atoms and the weights should be positive. And that's the idea of NMF. So you get the spectrum for the STFT signal, you get the spectrogram of the signal, and for every single frame, you should realize the way this is the fixed. This is already fixed. Offline, you pre-train the dictionary. You get the dictionary of the atoms, and you see that the weights are sparse. These are the entire weights, the dimension of the weights that should be, but you see that just sparsely there are some active weights that you can see here. But in general, this at every time instant should be close to the signal based on the divergence of Kullback-Leibler, and they should be both positive. That's the idea of NMF, and the story of BSS finished here.